Salamat sayang everyone. My name is Shelby Tommy. Today I'll be presenting quad band planar magnetic inductive waveguides for next generation wireless wearables. My co-author, Dr. Jayshree Kulkarni, is not here, but she was imperative in my research findings. As we move forward to next generation wearable waveguides, we're seeing that the industry is hitting a plateau. We need better systems. We need stronger systems, systems that support ISM and sub-6 GHz frequency bands while simultaneously being lightweight and flexible for wearable applications. One of the major challenges that we're seeing is that the industry is maintaining performance while the devices are unable to bend. We need devices that are be able to bend and be wearable, and especially in close proximity to human tissue. Our research has explored everything from 3D printed honeycomb models to dielectric models, belt loop shaped waveguides, and existing magnetic inductive waveguides have really hit the peak of their innovation. They mostly rely on single layer resonators, and this results in a weak magnetic coupling and poor field confinement. This vertically aligned configuration that we've created isn't just a minor tweak, it's a structural change and enhances the magnetic field confinement. Our design is a quad band powerhouse, supporting from 2.63 to 4.55 gigahertz. This copper band planar instructor system has achieved low wave behavior, ensuring that the signals stay focused. It offers multi-band performance and drastically lower specific absorption rates than current standards. It provides robust energy efficient solutions for stable body area networks, making it a lead candidate for the next generation of wearable communication and biomedical sensing. So for this section, we used copper and PET. Those were the things that we had available, but they work well in our simulations, and it indicated that materials can endure movement and bending on the human arm, and the SAW rate was not affected at all. The waveguide is excited through the central strip, and if you can see here in my image, the inner strip, that central strip, is excited from the set, like the left side to the right side, port 1 to port 2, along the periodic arrangement of magnetic resonant elements that is implemented with 13 on the top and 13 on the bottom, and they're perfectly matched, like in sync with the top layer and the bottom layer. A strong vertical magnetic coupling in this dual layer configuration forms a slow waveguide channel that effectively confirms electromagnetic energy and minimizes electrical field leakage. The strong inner magnetic coupling can produce 4 resonant passbands centered at 2.6, 3.25, 3.96, and 4.5 gigahertz. Each cell has around 12 by 12 millimeters with an inner coupling arm with a total length of 10 millimeters, including the effective coupling overlap of 9.3 millimeters with a central transmission line. The top and bottom resonators are separated by a 0.8 millimeter substrate thickness. So it is a very small component, but that's why it makes it so great for it to be wearable, because it's small and lightweight. When we talk about our reflection coalitions, the first resonance occurs at 2.6 gigahertz with a deep notch of negative 31 dB. So that off the bat, at our lowest, it's already going very deep. From 2.49 to 2.70, it's confirming strong magnetic coupling and excellent impedance matching. The second resonance at 3.25 reaches negative 22, so we're still, even though a bit higher, and we're still hitting those deep notches. While seeing as we go more into a higher frequency, the notches are not as deep, but they're still beyond standards. They're way past negative 15. So we're making those strides as well. So we're hitting 21 dB, negative 24 dB in operational bandwidth of 3.9, 4.3 gigahertz at this time. For our transmission coefficient now, we're staying very close to 0 as we're starting. So figure 3 demonstrates the simulated response for the proposed dual layer magnetic inductive waveguide, showing efficient forward transmission for all 4 resonant bands. Very low insertion loss and transmission levels of negative 0.23 dB and 2.6 gigahertz, or 0.34 dB at 3.25 gigahertz. So you would notice the trend as the frequency increases. We're slowly moving away from 0, but we're still very close to it. The H field. To highlight our magnetic inductive device behavior, the proposed dual layer waveguide we examine at the magnetic field of the X and Y plane, it's still constricted. It's still holding at 2.6, and it's holding even well at 4.5. To show in figure 4, A through D, each resonant band exhibits a distinct but well-confined H-field pattern. At 2.6 gigahertz, the field is tightly concentrated around each loop, representing the fundamental MI mode. As frequency increases 3.25 gigahertz, the field separates even more evenly across neighboring cells, indicating a higher order mode. At 3.96 gigahertz, distribution becomes even more intricate in alternating peaks, and by 4.5 gigahertz, the field is tightly compressed and sharper localized maximum. Importantly, across all four bands, the magnetic field remains strongly confined within the waveguide, which explains the consistently low loss performance observed. These results clearly demonstrate the efficient magneto-inductive energy transfer and confirm low loss multiband performance in the proposed structure. Finally, our SAR analysis. To evaluate user safety, we performed a SAR analysis. So we created a human model, a circular phantom model. So if you can see on the lower left side, we have the inner muscle, the fat, and the skin layer. So we use that model to then test our magnetic inductive waveguide on top of that. We used the proposed magnetic conductive waveguide and placed it 4 millimeters above the body sphere, like right above the skin. Both at 1 gram and at 10 grams, the SAR average distributions were examined as following the captured, like in our worst case scenario, the localized expression and the more partial spatially distributed absorption across the tissue. The SAR maps at 2.6 at 3.25 were shown in figures 5B and 5E. The higher frequency at 3.96 and 4.55 are presented in figures 6A and 6D. The frequency comparison all across four bands, the peak SAR values are well below IEEE standards. So even as we're running these tests at 1 gram for each of our our frequency passes, and at 10 grams, we're still really below those IEEE standards. Specifically, the maximum at 1G and 10G SAR values range from 0.47 to 0.96 watts per kilogram, and from 0.164 and 0.263, respectively, the frequency increases. Consistently low SAR levels directly reflect the magnetic field confinement of the dual layer structure, confirming that the proposed waveguide is well suited for a safe and continuous wearable. In conclusion, the work clearly demonstrates that dual-layer magnetic waveguides can deliver efficient, low-loss, and safe band operation for wearable wireless application. We can see that it's continuously showing us, even on human skin, great levels. It's able to bend, it's able to stick there. We don't have to worry about IEEE standards because it's adhering to that. Our magnetic field analysis confirmed confinement and stable execution of both fundamental higher order MI modes, which directly explain the low loss S12 and S21 performance, in addition to comprehensive SAR evaluations, both 1 gram and 10 gram, averaging the showed exposure levels comfortably below IEEE standards across all bands. Taken together, the proposed waveguide combines compact size and efficient multi-wave operation, strong magnetic confinement, and excellent safety performance, making it a strong candidate for next-generation wearable communication and sensing systems. Thank you so much. Thank you so much to Dr. Jayshree Kulkarni. Thank you so much to the board. Thank you to everyone who supported me during this time of research. If you want to see the rest of my research and the full paper, please scan this QR code and see the references at the bottom. Thank you.